Hi, today we're looking at section 3.5, which is exponential and logarithmic models. So we're talking about applications. You are going to need your calculator, so pause the video if you don't have it handy and grab that. And then anytime when we're working through these problems, if you need to pause it for a minute to enter it in your calculator to make sure you can do that correctly, don't forget you can pause it, make sure you get everything in there, know how to run your calculator. One of the things I can't tell you when we're taking an assessment over this is how to run your calculator, so you want to be sure that you are good to go. So first couple of things I want to go over are some models that we've talked about before, but we're going to go back over today and use the exponential growth model, which is y equals a b to the e to the bx, b's got to be greater than 0. We've talked about that. Exponential decay, so that has your negative exponent. We've talked about continuously compounding, which is that PERT formula. In previous classes you've studied half-life, and half-life is the time it takes for a substance to decay to half of its original amount. So that model, A is the final amount, A sub 0 is the initial amount, K is the half-life time, and T is the time that you're calculating. Logistic growth is the model that can have a rapid growth followed by a decline rate of growth. It's also known as the Sigmoidal Curve. This one I can tell you that we would not ask you to memorize that one. We'll give it to you in the problem if you need to use it. So in this model, A is the sample population, Y is the total population, and T is the time. A couple of reminders on the calculator. If you're going to do a regression, you go to Stat Edit and you enter your data in List 1 and List 2. You go to Stat and you go over to the kind of regression equation that you want and you choose that. So exponential regression will be 0. Then we're going to store the regression in y1 and calculate the regression that we enter. So we'll work through those steps. Then we'll turn on the stat plot, and then if we have to save anything, we'll be sure and store that, and then we can use that value in the next calculation. So the first one is just practicing kind of the regression. So I'm going to kind of go through that quickly because, again, you can always stop the video and then see, practice, anything like that. So this first one is about a population. So it's estimating the number in millions of U.S. households with digital televisions from 2003 to 2007. And it's shown in this table below. So we're going to create a exponential model using the regression tools. We're going to restrict the model from 3 to 7 for this particular problem. And then we're going to enter this in the calculator. So we're going to go to our stat menu. We're going to put the years in L1, and we're going to put the TV numbers in L2. But we're only going to do it says restricted 3 to 7. So instead of entering 2003, we're going to enter 2000. And we're going to enter 3, and then 2004 will be 4, and so on and so forth. So anytime you're doing this, remember you have to put the data in the stat list, you have to set your window, and then you have to turn on a stat plot or you won't be able to see it. So let's get that in L1 and L2. Alright, so we're going to take and put this data in. We're going to enter it into L1 with just the numbers. To do that, we do stat edit, and then we enter, so we press stat, we hit edit, and then we enter that information into list 1 and list 2. Then we are going to set our window. I'm just going to make it a little bit bigger than the biggest and a little bit smaller than the smallest. So I just went from 0 to 12 and 0 to 120. On the 0 to 12, I counted by 1. 0 to 120, I counted by 10. Restricting the domain to 3, 4, 5, 6, 7. That was just to let you know that you needed to enter these in as just single numbers, but I wanted to have a little bit better picture of my graph. You could have restricted it to like 0 to 8 if you wanted. Alright, so to calculate the regression, then we're going to go to Stat Calc. We're going to arrow down 3 times. We're going to do alpha trace to get the y1, and then we're going to enter twice to execute. So let's go through those steps. So we're going to do stat calc, arrow over to calc. We're going to go down to, well, I guess you could have gone up. Sorry about that. We're going to exponential regression. Pause there while I was thinking. So once we get there, we hit enter to execute that. And then we need to use L1 and L2, and we're going to store the regression equation. So to do that, we want to paste it into Y1. So we go down to where it says regression equation right here. We do alpha trace, and that pops up the Y menus, and we pick Y1. And then we go down to calculate and hit enter. And so it's calculating that regression equation as well as pasting it into Y1 in your calculator. Okay, so we've done that, but let's go back and look at the graph now. To do the graph, we put our list in stat edit Y1, Y2, or L1, L2, so we have that. Then we're going to set our window, which we did, and then we go second Y equals, and we make sure plot's on. It doesn't matter which of the four you pick. I just picked the first one, and it happens to tell me right here it's a stat plot, and we're using L1 and L2. So once I know that's on, then I can hit graph. The dots are my stat plot. The solid line is the regression equation that I just calculated. You can see that it's a relatively good fit. It's going through most of the, actually all of the points. Sometimes a good fit could be going through most of the points with an even distribution of the remaining points above and below. So if I want to get my equation, I can come in here. Remember that we can do, we do 3 decimals as our standard. So when I write the equation from my calculator right here, this is the whole thing going out, you know, with everything that's visible. There's more decimals there than I can see. But technically you could have said 30.915 parentheses 1.124 to the x power. And that's what I would have probably expected to see on your paper. All right, so the next part of B says, when will the number of digital TVs reach 100 million? So I'm going to press Y menu again. I'm going to go down to Y2, and I'm going to put in 100 for the 100 million. I'm going to graph. And just so it's not confusing, I'm going to go back to my stat plot, and I'm going to turn that off. You can do it from here, or you can do Y equals, and you see how the plot 1 is highlighted up here? You can turn it off from there as well. So we're going to graph so we can see the curve we calculated with the regression equation. We can see the horizontal line at 100 that's graphing right there. And when I can see 2 lines intersect on a graphing calculator, I can calculate that intersection by doing second trace, intersection. I only have 2 equations in here, so enter, enter to select the 2 equations. One more enter because I'm not really worried about guessing. And then I can see down here, the intersection at 100 million would be at 10.021. So you can say around 10.02 or 10.01, or you can say it would be in the year 2011. All right, so the one we're looking at now is number 2. It's the fruit flies. They're increasing according to the law of exponential growth. After 2 days, there are 100 flies. After 4 days, there are 300 flies. Create an exponential model to determine the amount of flies after 5 days. All right, so a couple of things here. Hopefully that you can see we have some data points here. 2 days, 100 flies, 4 days, 300 flies. We're trying to calculate the amount of flies after 5 days. So this is exponential growth. So the units that we're using are days and flies. So I always usually write that down so I don't forget once I get deep into a problem. And the model is a growth model, so I'm using that particular model. So what I'm going to do is take my 2 data points, and I'm going to create an equation using that growth model. And I'm going to rewrite them both to set equal to A, because that's what they both have in common. I have the amount for the A, I have 2B, I have a base of E, I don't know what A is. So if I set both of these equations equal to A, then with our substitution, then we can set both of those equations equal to each other, and we can solve for B. So how do we solve for B? We have to get the B's out, so I used and solved it proportionally. So I got 100 times this equals 300 times that, so that got my B's out from the denominator of the fraction. And then I divided both sides by 300 so I could get the numbers together. And then I divided both sides by e to the 2b to get the 3 by itself here and get the b's together on the same side of the equation. And we know from our exponential rules that if I'm dividing like problems that have like bases, then I can subtract the exponent, so that becomes 4 minus 2, which is 2b, which equals to 3. So how do we get the b out of the exponent? Remember, we practiced this. We convert it to an exponential. we convert exponentials to logs and logs to exponentials. Let me finish that thought. And in this case, since this is an exponential, it goes to a log. It goes to natural log because that's a base of e. And so I have this. So how do I get b by itself? Divide both sides by 2. And once I have this completely isolated, which these are the steps you will have on your paper, then I can go to my calculator and I can go to my home screen and type it in just like it looks, natural log of 3 divided by 2. I hit enter, I have a b value. So I'm going to actually store that in b. So if I go down here on my calculator to this button right here, which is store, I press that, I do alpha, and b is right here in green. And so once I see the answer is stored in b, then I hit enter. And once it pops over there to the right, I know that this is stored. And anytime I need to use that further in my calculation, I have my b figured out. Okay, so once I have it stored in b, then I'm going to use b to help me figure out the other parts of the problem. So in this particular case, now that I have b stored, I know that I have this equation set a equals, and I can pick either one I want to use from the beginning. Remember, we set them both a equals. I use this one because it was just smaller. And so then when I go to my calculator, I can type that into my home screen of my calculator using the b that I just stored by pressing alpha b, and then I'll get my answer. All right, so now that I have that in, you can see I use my alpha b right there. So I hit enter and make it happen, and that tells me what a is. So now I have a b value that I calculated and stored to begin with. I have an a value that I just found. So then I can go back to my basic exponential growth model using the information from the problem, which was, after 5 days, how much are we going to have, or how many flies are we going to have? So then I go back to my original model. I just calculated a, that's 100 over 3. I know what b is because I have that stored. So I can go to my calculator and type in y equals 100 over 3 e to the 5b. All right, so I just typed in what we've calculated. There's my a value I calculated in the last step. There's my b value I calculated in the beginning. And that tells me that that's approximately how many flies I have at that time. So like anything else, this is an application problem, and it doesn't make sense to count half or part of a fly. So if I'm writing my answer for this, I would probably say the amount of flies after 5 days is about 520 because it's a little over 519. But it would have also been acceptable to say the amount of flies after 5 days is about 519. It all depends on how you round, but you just definitely don't want to leave it as a partial fly. Problem 3 is a logistic growth model, and like I said at the beginning, if you have to use the logistic growth model, we'll include that in the test question, so you're not going to have this model memorized. You do need to have the others memorized, which you probably already do as much as you use them in Algebra 2. So there are 500 students, and one student has a very contagious flu virus. Suppose y equals the number of students infected after t days, and that's the model. So how many students are infected after 5 days? So when you go into your model, you're entering your 5 right here for the time. So you put this in your calculator, and you would get that approximation. I'm not going to go ahead and punch that in right now because really all you're doing is using your fraction template and plugging it in exactly like it is. So there's not much to that. So about 54 students are infected after 5 days. All right, so then in part B, how many days until 2,000 students are infected? So again, we go back to our logistic model, and we're setting it equal to 2,000 because remember it equals the number or final amount. And so you're going to work on your paper to isolate t. So I would multiply both sides by the denominator to get t out of the bottom. And then we're trying to get to t. So I divide both sides by 2,000, which gives me the fraction 5/2. And then to get to the t, I move the 1 over because we got to get down to this term right here. And then once I move the 1 over, then I can continue to isolate. So once I get to this point, to get the t out of the e right here, remember that we have to convert it to a log. So we're going to go ugly, yes, but convert anyway. So we get the natural log for the e, this whole ugly fraction, which I would personally just leave like that. There's no sense in making an error when you're entering your calculator when you can make it look exactly like this when you punch it in. And then we would divide both sides by -8 to get t by itself. If this were a problem for me, I would expect to see how you got down to this, and I would not expect you to go into your calculator until this is physically on your paper. Once you go into your calculator, you can literally make it look just like this. Make a big fraction, put the ln in the top. Make another fraction, make a fraction in the top of that. Put the decimal in the bottom, divide by negative 0.8. And since you're calculating, it's okay to have the negative on the bottom here. But remember, under normal circumstances, we put the negative in front or we put the negative on top. So this is what we get. So we get to interpret our answer. So T is approximately 10.139. So after 10 days, 2,000 students will be infected. Question 4 is compounding continuously. So we have an initial amount at 600. We want to know what it's going to be after 10 years. The value is this after 10 years. What was the rate that was used to make that? So we want to find out when it's doubled, and we're looking for the rate that it took for it to double. Okay, so that's definitely the compounding continuously formula. So we're going to plug in to find the rate. We're going to put in the amount at the end of the 10 years and the initial amount. We don't know what R is, so now we use our steps to find R. So we are going to get this piece by itself, so divide both sides by 600. Then we're going to change it to a log, so it's base E, so it's natural log of all of this, which is 19,205 over 600 equals to 10R. To get R by itself, we divide both sides by 10. So you will have this on your paper. And then we can use the calculator, punch it in to figure out what R is. So once we figure out what R is, then we're going to store it in the calculator. So press the store button, alpha R. And so this is what we're storing in there, but remember, this is what it means. The rate is 34.660. So we're storing this, we're interpreting this, okay? Now, part 2, we need to find the time it takes to double. So all of this was the given information in the problem, and we use that given information in the problem to figure out what the rate. Now that we know what the rate is, we can go to our exponential model and figure out what or how long it's going to take it to double. So if it starts at 600, it doubles at 1200. Be very careful here. I always get students that don't double the right amount, or they aren't thinking about it, end up tripling amounts, things like that. So 600 I start with. If I want that to double, it has to be 1200. We have the rate stored as R, so we now have 2 equals E stored rate T. So I know that I need to get the T out of here to solve for it. So I'm going to convert it to a log. So natural log of 2 equals RT, and then remember R is a number, we've just stored it. So we're going to divide both sides by R. So to find out T, this is what I put in my calculator. And when I make that calculation, I get this. So the money will double in about 2 years, because at 1.9998, pretty darn close to 2 years. All right, our last question, number 5, is a half-life practice problem. A half-life of carbon-14 is 5,715 years. 2 grams remain after 1,000 years. Find the initial amount. So initial amount means I'm trying to find the beginning amount, or the amount it started with. This right here is your half-life cycle. So it takes 5,715 years for the amount of that carbon-14 to be half as much as it was to begin with. So I go to the half-life model. Remember, this A sub 0 is initial amount, final amount, T, and K. Okay, so T grams after 1,000 years. Half-life cycle is 5,715 years. These are things that you want to think through so you understand where they go in this particular model. We're going to calculate it after 1,000 years, and we want to find the initial amount, this one right here, the starting amount. Okay, so then I put what I know in my model. So this is the amount. We have 2 grams remain after 1,000 years. 1,000 is the time you're calculating for. The 5715 is the half-life cycle. So it's the amount you calculate for over the whole cycle. Just think about it as the meaning of a fraction. Fractions are part over the total. This is the part I'm calculating for. This is the total. So if that helps. The base is 1/2. Well, it is called half-life, so there you go. And if you have A sub 0, that's the initial amount. That's the unknown. So to get A sub 0 by itself, we need to divide 2 by all of this stuff right here. And once we have A sub 0 by itself, we go to our calculator and we punch it in. And so I should be able to get a fraction template, put a 2 in the top, go to the bottom of the fraction, you could either do 1/2 as a fraction, or you could do 0.5, exponent key, and then put your exponent in as a fraction. I can't tell you how important that is. Over the years, I've seen so many students lose points on questions in exponential and log model problems because they don't get stuff in the right spot. So with this new template where you can make everything look exactly like you intend it to, please do that. If no other reason, just because it's maybe going to keep you from missing a problem you would otherwise get right because you know what you're doing. You just entered it into the calculate incorrectly. So here's what I got. And so when we interpret the meaning, because this is an application problem, the initial amount of carbon-14 was about, that about keyword is important because we are approximating, 2.258 grams. And what was that again? That was what it started with, and we were calculating when the amount was 2 grams after 1,000 years. So it's not quite to half as much, but we're using the half-life model to get us to this calculation. All right, so that should take care of all of your problems in this section. They're all practice application problems. Remember, the rules are when you're doing an application problem, list out what your information is in your model, write down the model with everything in it appropriately, use your analytical steps to solve and get whatever the unknown is you're solving for by itself, then go to the calculator and make your calculations. Thanks, guys. Bye.